Now thin lens, right? So thin lens formula, what I'm going to do is I'll take this. This is equation number 3, and I'll take this equation also. This is equation number 4. This I'm going to take this as equation number 4. All right, and I compare equation 3 and equation 4. All right, compare equation 3 and equation 4. All right, compare equation 3. I'll rewrite equation 3. Let's say let's rewrite equation 3. What is that? 1 by OB plus 1 by DI is equal to N2 divided by N1 minus 1 by BC1 plus 1 by GC2. This is equation number, rewrite equation number 3. And then the equation number 4, I'll write equation number 4. What is equation number 4? Equation number 4 is 1 by F is equal to N2 divided by N1, then 1 by BC1 plus 1 by GC2. This is equation number 4. All right, so this is, I say, this is equation number 5, and this is, let's say, equation number 6. All right, and then I compare equation number 5 and equation number 6. Comparing equation 5 and equation 6, what I'm going to get is comparing equation 5 and equation 6, what we get is 1 by OB plus 1 by DI is equal to 1 by F. F is focal length. Alright, again I am going to use the sign convention. Sign conventions. OB is minus U. Alright, and then DI is minus V. Not minus V, then 1 by minus U plus 1 by V is equal to 1 by F. Alright, so therefore finally I write V equal to U equal to 1 by. Finally 1 by V minus 1 by U is what we call as thin lens formula. This is what we have is thin lens formula. Designed. Alright, so this is what we have. So this is what we call as thin lens formula, and this is what we call as Lenz-Megal formula. Alright, this is what we call as thin lens formula, and this is what we call as Lenz-Megal formula. Now you may ask me, what is the difference between the thin lens formula and Lenz-Megal formula? Thin lens formula talks only about image formations. So why? Because here you have, this is image distance, this is an object distance, F is a focal length, and focal length tells about nature of lens. Focal length tells about nature of lens. So this tells about only image formation. This gives you an idea about image formations. And what about Lenz-Megal formula? A Lenz-Megal formula tells about how to design, right? how we designed or what kind of lens. How we design what kinds of lens. Alright. And then one more important point is that two formulas are valid for convex lens and concave lens. This is valid for convex lens as well as concave lens. This is also valid for convex lens as well as concave lens. Alright. So these are the two very important formula, important concept for examination also. Thin lens formula and lens macro formula. The name itself tells you lens macro formula. That means macro means how you design lens. How you design lens. So what you do is after this lesson, what you do is you write your notes, separate notes for lens macro formula, and you write separate notes for thin lens formula, so that in exam you will not confuse. All right. Now next I would like to discuss the image formations. All right. And normally last time also I told you that mirror formula and lens formulas also tells you about image formations. So this tells you about image formations, right? So therefore I will give you before I start image formation, let's talk about three types of ray. For convex as well as concave lens. This is done in a lower class just for small recapitulations. So the rays are this. First ray is normally there can be an infinite number of rays. However, we divide the ray into three important rays for image formation. So first is the rays are parallel to principal axis. If the rays are parallel to principal axis, for a convex lens, the refracted ray or emerging ray pass through focal length. And for a concave lens, refracted ray appear passing through focal length, extended refracted. If I extend the refracted ray and refracted ray pass through focal length, this is the first ray. And the second ray is this. When the ray pass through a focal point, one focal point, this is the first focal point, then the refracted ray is parallel to principal axis. Likewise, for concave lens also, if incident ray appear passing through a focal point, alright, second focal point, then refracted ray is parallel to principal axis. And the third ray is when the ray pass through optical center. This is what we call as optical center. When the ray pass through optical center, no deviations. Alright? There is no deviation. Why? Because ray is passing through a normal line. Why? If you ask, the ray is passing through a normal line. Likewise, for concave also, when the ray pass through our focal optical center, no deviation will take place. So now again, image formation. This is just a recapitulation, all right, of class 10. This is for convex lens. If an object is at infinity, image forms at focal point, and then image is going to be highly diminished. And object lies between infinity and this infinity and a 2f1. Then image forms between 2f. This image forms here 2f2 and 2f2. So image is diminished. It is real image. All right. If object is at 2f, image is formed at other 2f and same size, again inverted, and it is real image. And if object lies between 2f1 and f1, image forms between 2f and infinity. All right, and image is enlarged. And now, if object is at a focal point, image form at infinity. All right, and last, if an object lies between f1 and optical center, this is what we have. For convex lens also, you have one virtual image. If an object lies between F1 and optical center, image is a virtual, image is always inert, erect, alright, and image is formed between infinity and F1. This is for convex lens. Now concave lens we have here. These are the recapitulation, class 10 recapitulation, right? And this is the object is at infinity, image appears at focal point. That means it is a virtual image. If object lies between infinity and our optical center, image is formed here. And then this is what we have difference. For a convex lens, image there can be a virtual image, and virtual image is always inert. And for concave lens, it is always virtual image, and the image is always diminished, either highly diminished or diminished. Alright, these are the image formation. And then one more I would like to tell you is, and the entire image formation we discussed just now, alright, can be explained using this formula. Alright, and now let's talk about rectification, right? You can take any image formations. Let's take these image formations. This image formation. Let's take this image formation. When I take this image formation, I take these two triangles, right? This triangle, right? Now let's talk about magnification, right? Magnifications. We know definition of magnification, right? Magnification definition is ratio of height, image height to object height. This is magnifications. Now I take the two right triangle, alright? Right triangle A, O, B, and right triangle A prime, O, B prime. And these two are similar triangle. These two are similar triangle. If these two are similar triangle, the ratio of corresponding sides are equal, right? So what is that? This is equal to what is that? B prime, A prime divided by B A is equal to O B prime divided by O B. Alright, now I use the sign conventions. This is going to be a minus H prime. Why? Because inverted. This is going to be H, and this is going to be a plus. This is V. This is going to be a minus U, and these two cancel out. Finally, I get H prime divided by H is equal to V by U. And what is H prime by H? Is magnifications. So magnification is H prime divided by H, which is equal to V by U. Therefore, I can figure out magnification even in terms of object distance and image distance. So for magnification, I have a two formula. One is this, and other one is V minus U. Alright. Okay, now you go and discuss the image formation, virtual image and the real image. Alright. So this is home assignment again. For virtual image, what is going to be our rectifications, and then what is going to be a sine of V. For a real image, what is going to be a sine of N, and what is going to be a sine of V. Alright. So this is all about lens. Now I would like to discuss power of lens. Now I would like to discuss power of lens. So discuss power of lens. Alright, now if I ask you a question, what lens does if ray falls on a lens? So if I incident a ray or a beam of light on a lens, what lens does? Alright. So we say two things, right? Either lens converges, either lens converges or lens diverges. Alright, therefore in a lower class we say that one lens is called a converging lens. Converging lens. Other lens is what we call as diverging lens. So what is the role of lens is to either converge or diverge. So now what is power of lens? So the power of lens is what we define as it is also defined as the measure of degree of convergence or divergence. It is the measure of a degree of convergence or divergence. If a divergence is more, then power is more. If a convergence is more, power is more. Alright? But these two are opposite, right? Alright, that means this is normally done by convex lens. This is normally done by concave lens. So converging in nature, diverging in nature. Alright. So therefore I'll give you one diagram. Let's say I have this. This is a lens and I have a principal axis. This is principal axis. Let's say this is F. This is 2F. This is F prime, 2F prime. Look here, now I incident a light. Then this is a parallel ray and light. This is refracted ray. This is delta is convergence. This is what we call degree of convergence. This is a degree of convergence. If this degree is more, then lens has more power. If this degree is less, lens has less power. And again, we define this as power as, look at here. So therefore we define power of lens as is defined as the tangent of the angle, tangent of the angle at which beam converges or diverges. Alright, when incidence falling, I say falling at unit distance from optical center. That means this distance is 1. This distance is 1. Alright, so tangent of the angle at which beam converges or diverges when falling at a unit distance from optical center. So this is what we define as again power of lens. So having this definition, I just write here, tan delta is going to be, let's say tan delta is what we call as height divided by focal length. Alright, So since I choose f is h is equal to 1, then tan delta is equal to 1 by h. So since delta is small, delta is equal to 1 by, this is f. Delta is what we call as f. And this delta is since the degree of convergence or divergence. So this is what we call as p. So p is what we define as f. So maybe in the lower class you might have defined power as reciprocal of 1 by f. Power is defined as reciprocal of 1 by f. This is what we define as power. So therefore we say that the degree of divergence or the degree of divergence or degree of convergence are more if f is less, right? So therefore we say for small f, p is more. So for large f, p is less. So if a focal length is small, then power is going to be more, and for a focal length is large, power is going to be less. Again, now how you identify whether it is converging or diverging, right? So whenever it is diverging, power is going to be negative, right? And whenever it is converging, power is going to be. Why? Because this is all defined by f. Alright. So I will write here for convex lens, f is positive, which implies p is positive. For concave lens, f is negative, p is negative. So this is how, alright, this is how we differentiate whether it is a convex or concave using power. And what about unit of power? Unit of power, SI unit of power is diopter. SI unit of power is diopter. That is 1 d is equal to 1 by 1 meter. This is what we call as 1 per meter. So if I say if a power of lens is plus 1 d, which implies it is a convex lens having 1 meter focal length. Convex lens having 1 meter focal length. Alright? And then if power of lens is, let's say power of lens is minus 2d, which implies again it is concave lens. Why? Because power is minus, and focal length must be what? Focal length must be smaller, right? So focal length is equal to half meter. Alright, this is all about power of lens. Now we will talk about a combination of lens. Of lens. Alright, so this is the last topic I'm going to do now. So how to combine lens? So combination of lens when lens are in contact. So I'll consider two concave lens, convex lens. Lens A, lens B. Lens A having a focal length f1 lens B having focal length f2. Now this is principal axis. Alright, this is an object. This is object, and then this converges. This is O. Let's say this is I1. Now look at here. This is going to be V, U. This is going to be V1. All right. So for lens A, all right, object distance is equal to object distance is U, and then image distance is V, and the focal length is F. Therefore, what about the thin lens formula? 1 by F1 is equal to 1 by V minus 1 by U. Since V is V1, I'll just say V1. This is for lens number 1. And then lens number 2, now I'm going to say. For lens number 2, now it is going to further converge. This is I. Alright. So lens number B, lens B, I1 act as an object. I1 act as an object, and I is image. I write here final image. Alright, I say it is final image. Then what about lens formula? 1 by F2 is equal to 1 by V minus 1 by U. This is what we have. Lens 1, lens 2. Alright. Now finally, what about combined lens? This is for lens A, this is for lens B. Now combined lens, I write here, combined lenses, this is the focal length of combined lens. And then, what about this, object? Object is going to be a U, and image is going to be, a final image is going to be. Alright, this is what we have. And then what I'm going to do here is, I'm going to combine these two, right? We will combine these two, right? This is going to be not U, this is going to be V1, right? So how to get this? Very simple. I combine these two. Let's say this is equation number 1, this is equation number 2. I add up these two equations, then we will get these equations. Adding equation 1 and equation 2, 1 by F1 plus 1 by F2 equal to 1 by V1 minus 1 by U plus 1 by V minus 1 by V1. Then these two cancel out. Finally, what we get is 1 by F1, 1 by F2 equal to 1 by V minus 1 by U, and final equation, this is this. Alright. So I compare these two equations, right? This is equation number, let's say equation number 3, and this is equation number 4. I combine these two equations, finally we get this is how we combine. Alright. And then what about the power of length 1? Power of length 1 is going to be 1 by F1. What about power of length 2? F2. So therefore, total power is equal to P1 plus P2. Alright, this is power of length. Alright. So magnifications we will do next class. Alright. So magnification will do next class. Next class I will do a small recapitulation of this, and then I will continue with magnifications. So I've given you that assignment. that is how to get refractions through a second lens. Now this is how we find a power. P is equal to P1 plus P2. If I have n number of lens, power can be written as P1 plus P2 plus P3, go on, right? You just add up. And then one thing you should keep in mind is that if I combine a convex lens and a concave lens, then these two cancel each other. Why? Because the power for convex lens is positive, the power for concave lens is negative, right? So if I have, so therefore the power of lens could be something like algebraic sum of power of individual lens. I'm going to repeat. Power of a lens, the total power of lens can be obtained by algebraic sum of power of individual lens. Alright. Now if I do magnification, power is done. Now magnification, right? Magnification is defined by V by U. Alright. Again, magnification is defined by H prime by H. So having this now magnifications, so this is the magnification of a total lens, our combined lens, and I just say divide and multiply by V1. Divide and multiply by V1. Why? Because V1 is an intermediate state. V1 acts as an object for second lens. Alright. So therefore having this, now V1 by, look at here, V by V1 is magnification for the second lens, and V1 by U is magnification for first lens. Alright, therefore, if I combine, magnification is equal to M2 into M1, this can be written as M1 into M2. If I have n number of lens combined in contact, then magnification is for n number of lens, lenses, magnification can be written as M1, M2, M3, so on. This is how we get magnification, right? This is total magnifications, and this is combined. So in short, when we combine the lens, all right, the magnification is the product of its individual lens. Unlike power, when we combine the lens, the net total power is algebraic sum of its individual power. All right. So finally, I will do, if I have convex lens, let's say I have a convex lens like this, a small problem, and then I combine this with a concave lens. Alright, convex lens, let's say this focal length is, let's say 1 meter, this focal length is plus minus 1 meter, this is converging, and this is diverging. Then if I allow a light to pass through, light never undergo any converging as well as diverging. Why? Because what is the total power? Total power is equal to plus 1d plus minus 1d, so power is 0. Power is 0, which implies it is a plane glass. See this? Plane glass. That means there is no duration, right? There is neither convergence as no divergence, right? So with this, I finished thin lens formula, and then lens maker formula, and then the power of lens, and then about the combination of lens. Alright, so with this we come to an end of entire lens. Alright, so next class we are going to discuss refraction through prism. Alright, so next class we are going to discuss refraction through prisms. Alright, So you do that home assignment. Reflection of light through second surface. Thank you.